So thank you very much for the introduction. I will say in all modesty that, my intro condensed like 20 years of stuff into like 4 paragraphs. So it's not like I'm doing all that all the time. All right, so I'm glad we were able to show the video to kind of kick this off because our time is definitely limited. So I'm going to move through this fairly quickly. I'm going to hand off to Dylan at certain points, and then I'll come back in. But essentially, this was a project that is located in Sri Lanka. So everyone kind of has a sense of where that is. Very close to the equator, essentially off the coast of India. And we were talking in our discussion group about some other sort of tropical humid projects as well. But the real consideration climate-wise is humidity. The temperature range, as you can see in the kind of gray band, is actually quite narrow. And it's just really humid all the time, hot and humid all the time. The project itself is located in an industrial park, which is adjacent to the airport. And that was really critical for a number of reasons, primarily because it's a tax-free zone. So we were able to, bring in all of our specialized materials without, any kind of burdensome duties or taxes. This was the existing building, so it's a retrofit. It was a factory building before, a very simple building with, steel frame and a metal roof. And you can see a little bit of the context. It's kind of a low-rise industrial park. There was a little bit of shading from trees, but not much. The interior was, basically exposed steel, a few partitions, 2 floors. This is the bottom level. The upper level is kind of cool because it's just very big, wide span, open space. There was all this old ductwork in there, which was unfortunately detracting from appreciating that ceiling height. But again, a kind of interesting building to be working with in general. One thing I do want to bring up is, and I think this is really important to appreciate when we're dealing with other cultures and other climates, there was an expectation that carried through to the programming of the building that some of the spaces would be outdoors. And when I say outdoors, not outdoors in a field, but literally considered as, untreated, unconditioned, even within the building envelope. So that was one of the challenges we faced, was really working in, where that enclosure line was and how to provide people the ability to have these programs in temperatures that they would find more comfortable than, for example, being in a cold air conditioned building. So our project started with a feasibility study. This is a quick diagrammatic section. This is a cross section, and you can see that upper level, which is clear span. And one of the things that you can see here is that the envelope on the lower level is actually pulled in from the edge of the enclosure. So we gave up space at the edges on the lower level in order to provide for shading. And we work with a local architect who actually had done the schematic design for the building, and it was very important for him in terms of his design scheme that he should have, some trees and other foliage that would actually be growing underneath the roof. So this is a plan of the lower level, and the blue indicates the treated floor area. And you can see already on this floor, there's some toilets and security check-in, as well as the canteen that are actually outside of the treated floor area, outside of the envelope. And on the upper level, it's basically a giant production floor. So there's rows and rows of sewing machines. There's also cutting tables. And one of the main issues that we dealt with here as well was the heavy process loads that were generated by all of the specialized equipment. So not only the sewing machines, but there were steam tables and fusers and all kinds of industrial machinery, which was running pretty much all the time, generating heat and humidity within the building, even beyond the occupants of the project. So some of the challenges we faced, we had a very bare bones kind of schematic set of drawings to go off of. We didn't have a lot of information in terms of the historic energy loads. Obviously no 475 in Colombo, so there was nowhere to get a lot of the materials that we needed. And the building itself was, had complex occupancy and usage patterns in the sense that it would be on and off, maybe 2 weeks on, 1 week off, maybe 18 hours a day for a week, maybe 3 hours a day for a week. So really getting a handle on, the actual occupancy and usage was a challenge. We knew we wanted to go for EnerPHIT. So that was, the goal that was set out early on. And we also knew that, given our interviews with the clients, that they had very specific expectations in terms of the treated and untreated area. The local architect was really keen to maintain the aesthetics of the exposed steel. And our agenda was certainly to create a model that could be replicated and ideally perform some technology transfer so that we would have skilled people on the ground who could then be ready for the next project. The feasibility study showed that we were looking at a potential 77% reduction in primary energy over a baseline, and we were hoping for a 6 to 7 year payback period, and we came pretty close to all of this. I'll hand it over to Dylan now, and Dylan, maybe you can just give me a heads up when you want me to go to the next slide.
Sounds good. So yeah, there's some questions already that were coming in about whether or not there were heating degree days, what are the cooling degree days. So as you can see here from the PHPP, these are in SI units, and there is only a cooling demand that we were required to meet the thresholds for. On this specific project, we certified using the cooling load threshold, and you can see that it's very high, even for the typical pass spouse project. And there's a couple of reasons for that. One is the climate itself. So the PHPP has a sort of adjusted threshold on the cooling side if your climate is hot and humid, and that it'll essentially adjust when you have more of a dehumidification load or a humidity load in that climate. So that's one of the reasons why it's so high. But it also adjusts when we have high internal loads in the building. So we'll get into this in a minute on how much internal loads and process loads go into a building like this, and that's contributing to it. So we were really balancing sort of unusual numbers in terms of trying to meet cooling loads, but the PHPP was a great tool to allow us to do that. Next slide. So this is the summary of the primary energy, so our source energy used by end use here in kilowatt hours per meter square per year. And you can see cooling is the biggest chunk of this at 27% of the building. Dehumidification is also a large chunk of that as well at 7%, particularly in those monsoon seasons when the humidity is pretty high almost all of the time. In those months, that's where the dehumidification loads are the most significant. But you'll see here at 20%, the sewing process loads are the next biggest chunk along with lighting. And these were the hardest loads to quantify and get right in the model. So we have some images a little bit later of some of these equipment setups and banks of equipment. But one of the things that we found was extremely useful was we went on site with JPDA's team and with our team and visited the project during construction. And we got to see some other facilities that have similar process loads and similar equipment. And what we actually did is, like, when we were setting up the model, like, I didn't know how long a sewing machine typically runs for. So we asked like a general question to the team, hey, can you send us a list of all the equipment? Can you tell us what the nominal power draw of that piece of equipment is? But then we need to estimate how long it runs, because it's not going to be running at that full load year round. We're predicting annual energy use. We're not just predicting a load. So we need to know how often it runs. And that was the hardest part, how often it runs. And one of the things that we looked at was quite literally how often the workers were pressing the foot pedals on the sewing machines. And we did like a sampling of, like, for 2 minutes, how many, they stepped on the foot pedal for like 15, 20 seconds. And that was sort of like the level of research that went into like sort of quantifying a lot of these loads. But as we'll sort of foreshadow into the future, we actually were pretty darn close with what our estimates were. So, but yeah, sewing process loads is a huge chunk. And then it's, as Jordan mentioned, it's also an office. So PC, office equipment, and lighting are a huge chunk of that as well. Next slide. So one of the things we looked at is, because there's such a high dehumidification load in this climate and in this building particularly, cooling and the strategies to not only cool but also dehumidify are a huge part of the building's energy demand. And one of the things we looked at was, in a typical cooling system, when you want to really dehumidify air, you have to super cool that air and condense all of that moisture out, so the moisture in the air can condense on the coils, and then reheat that air. So you're doing a lot of reheat. And the reheat is kind of the tricky part in this equation. And the norm in this region is to reheat your air, your recirculation air, with electric resistance coils. And if the dehumidification load is significant, that can be a huge chunk of energy. So we looked at alternative approaches to do that. One of these approaches is a system that has been around for quite some time, but isn't really used on many projects per se. It's used on more unique industrial type projects, and that's a solar charged desiccant system. So you basically have a desiccant that's absorbing moisture, and then you sort of evaporate it out with a solar thermal system, solar panel system. But the challenge with that was it required a significant amount of roof area that, quite frankly, we didn't have a whole lot of real estate, and would have ate into our ability to have PV on the project. And it was also sort of not a familiar system, and one that, there was a bit of a concern with ensuring that it can work properly, as opposed to some conventional alternative systems that we felt could work better. So we ended up not going with this specific approach. Next slide. And here's a shop drawing of what was originally intended. And this is actually for the project before we sort of got our hands in it and got to comment on it and tell them that this is not a great strategy in terms of energy efficiency. And this is, what we're looking at here are those reheat electric resistance coils at their VAV boxes. And that was their basis of design, essentially, until we looked at alternative solutions. Next slide. Next slide. Yep. Okay, so what we ultimately arrived on was a wraparound heat pipe to do the reheat. So what this is showing here is in the main air handlers for the building that has our cooling coils and are doing the majority of the cooling in the building, particularly on the upper floors where they have all of the people and equipment. There's a heat pipe that absorbs heat up from the incoming air that's already hot and warm, and it takes that heat and it moves it over here after the coil. And once that air gets not only cooled, but also super cooled down to that temperature where they can condense all that moisture out, now we're just using that recovered heat that was, quite literally wrapped around the primary cooling coil to reheat that in. And that provides a significant savings for the project. Next slide. So here is sort of an analysis that we had done looking at an electric reheat scenario on the left versus the heat pipe scenario on the right. And you can see the primary energy demand dropped from 421 kilowatt hours per meter square per year down to 344. So a significant reduction in both source energy use and also, as we show below, annual energy consumption of about 108,000 kilowatt hours per year, which translates to roughly $8,000, which is certainly not nothing, especially in a climate in a region like this. That's certainly a huge chunk of savings. Next slide. I'm going to hand it back off to Jordan.
Sure. So I'm going to talk a little bit about some of the basics of the design strategy. So again, you'll see there's really nothing new here that you guys haven't been thinking about all the time. Potentially the only, really significant change is, being so focused on mitigating solar heat gains. So, we've got a lot of roof here, so reflective roof paint is a no-brainer. We've also got a few PV panels on the roof, but not that many. But the heart of the system, as you would expect, is insulation continuously all around, continuous air barrier, and then our energy recovery ventilation. So we're doing all the things you'd be doing pretty much anywhere else. We're just doing it in Sri Lanka. There's some additional factors that we have here. We have like perforated metal screens we're using as solar shading to cut down some of that solar heat gain. And we already talked a little bit about architecturally how these overhangs were used to, again, sort of provide more shading for the lower levels. But again, it's all pretty straightforward stuff by the book in terms of your design approach. I was talking earlier about sort of cultural appropriateness and really understanding kind of what you're going to be faced with in terms of a successful build. So none of us had ever built in Sri Lanka before. we didn't have a huge sort of comfort level with the level of skills and also the material availabilities. So we really tried to engineer the system to, when I say the system, I mean the enclosure, to be able to be built up using very basic materials, applied, mostly with hand tools, in a way that was, as forgiving as possible. And so, you can see this is one of the mock-ups that was built on site. But we've basically got a liquid applied air barrier that's going over, in most cases, masonry. And then we've got foam insulation and a basic EFIS kind of system with layers of stucco on top of that. And that's what you'll see in most of the solid walls. Our roof was basically a insulated panel roof, pretty basic with reflective roof paint. And so again, we're just trying to maintain our continuous insulation, maintain our air barrier. Yes, we have some tapes, and we have a few fancy materials that I'll show you in a minute. A mock-up that we did in the office using like found materials around our desks to kind of explain some of the logic behind the window install. It didn't actually even follow this in the end, but we tried to use every technique we could to really simplify and explain, for the contractors who, had no high performance building experience, what was going to be required and the different, kinds of material connections and integrations that they could expect on site. We have a few details here. I'm not going to spend a lot of time on them, but we can come back during the Q&A. Mainly what we're showing here is we had some interesting conditions, like for example, where we talked about pulling back the enclosure. So we had some areas that were actually, within the building, but outside of the thermal envelope. You can see the green here that's highlighted. That's actually where we applied Airlon as a thermal bridge mitigator. We had some purlins and other elements that were actually sticking out through the edge of the envelope. And beyond that, it was pretty conventional stuff. Some of our kind of early window details here. One of the challenges as well was that we basically started off with almost no details. We had to make most of these up ourselves. Kind of somewhat guessing and asking for information about what was on site in terms of the existing conditions. And then even once we had our details, because there were many levels of communication going on, we would often find out that actually some of these details had changed without our knowledge, and then we'd have to kind of scramble to catch up and make sure that we had appropriate strategies for mitigating thermal bridges and other issues that were going to be potential issues. Suddenly structural steel became very cheap, and so there was all kinds of structural steel all over the place that we had not anticipated. Okay, I'm going to keep moving here. Again, sort of a roof connection, showing some of those sort of tricky moments. And Dylan will explain to you later how this was almost our Achilles heel for the whole project. Construction. So, as we talked about from the beginning of the presentation, this was an adaptive reuse, and as the video mentioned as well, the goal here really was to preserve as much of the structure as possible. So we preserved the floor slabs, preserved the steel frame. There were some modifications. We did do new roofing because there was, basically nothing that was usable in terms of the roof. Here you can see some of the roof panels going up and the view from the roof. It's pretty hot up there. Here are the roof panels themselves, nice big foam roof panels. And here you can see the steel frame going in. So there were some extensions to the existing frame, but pretty basic. Here's our Airlon moments where we had some penetrations, and we we're very eager to try different technologies and different materials to see what we could do to mitigate some of the thermal bridging. And it helped a little bit. We also have some a GP block here and there where it was appropriate, but we certainly weren't sort of throwing these things around. This is a great photo, which really I think sums up in one photo the state of what a lot of the world considers to be typical construction. So yes, we have a steel frame, but all of the exterior as well as a vast majority of the interior partitions are being done in masonry. Masonry is a technology that has existed for thousands of years. It's cheap. It requires fairly low skilled labor, and the bricks are manufactured almost everywhere. So we knew going into it that there would be a lot of masonry. I think we were surprised at how far they carried it, really how much masonry they ended up using, particularly, in some of these interior partitions where we just never would have imagined that would have been the case. So here's a liquid applied air barrier going on top of the masonry. And I think, this was so great in terms of having a material that, could be easily applied and also had a really strong visual component to it. I mean, you could really see where it was and where it wasn't. The foam going up on top of that liquid applied air barrier, and then of course wrapping around underneath on those overhangs. And then again, another photo which I think, is very telling. Not a lot of protective footwear happening in Sri Lanka, but this is the state of the construction industry in big chunks of the world. And I think if we're going to do high performance buildings outside of North America and Europe and Australia, you have to be able to work with what the industry is, what the technology is, what the skill set is. And, we were happy to see scenes like this because it meant that they were doing what they should be doing, without too many difficulties. Glazing was a big challenge on this project, and Dylan will talk about it in a minute. But you can see it was kind of an infill system, and it was a lot of back and forth on, where we were going to get the frame from, where we were getting the glass from. This was one of the big challenges, because everything had to be imported. And so lead times and cost were certainly, big considerations. There was testing, which Dylan will talk about in a second. And I will hand it over to Dylan for that.
Yeah, so as I mentioned before, we went out about halfway through the project when they were in construction to do some mock-up testing, or sorry, not mock-up testing, but testing on their first sort of installed window and curtain wall systems. And it was a useful test. We brought a fog machine out and we were there with the contractors to show where leaks are happening. And we did identify leaks and had to kind of come up with some solutions in terms of sealing tricky areas in the curtain wall where it's just, a 3D condition that you just can't draw and simulate reality in a lot of ways. So we had to sort of address some issues in the field, which was really helpful. But one of the things we did, and this is something I think is extremely valuable on any project, but particularly on a project like this, put together QA/QC construction checklists. So we put together a typical checklist for more repeated areas on insulation thicknesses, making sure that's maintained, air barriers installed properly, any tricky details that need to be taped or sealed. We highlight all of that and review that, go through that with the contractor. Next slide. And we also do some unique conditions as well, unique checklists. So, and again, the idea too is to really just walk through with the contractor to identify not only what the detail is and how it will be executed, but also when during construction it will happen. So that way, if there's any sequencing issues, those can be hashed out before the project is sort of in critical mode when it's actually being built in the field. Next slide. This is a photo of our testing on one of the curtain wall systems. And as I mentioned before, it was a useful test that we were able to find leaks and troubleshoot and address. And that was definitely very valuable to the project. Next slide. This is that crazy 3D condition that we have some tape, sort of air sealing tape fastening back to the backup wall and tying into our curtain wall frame. And this specific 3D condition where the center mullion meets the sort of transoms at the top was just a source for leakage. And we basically just had to goop some sealant in there and address that the best way we could because it was a repeated condition on the project. Next slide. So one of the fun things about this project is myself and one of my colleagues, Mike, became DHL global freight experts because we had to ship blower door equipment across the world, and that's not easy. And we actually looked into getting equipment shipped from either Germany or other areas in Asia, and that was extremely expensive. So we basically put our equipment on a slow boat and sent it out for a month in advance. And these are the primary forms of one of the main forms of transportation in Sri Lanka are called tuk-tuks, and they're fun to ride in. And this is some pictures of our equipment in the tuk-tuk. But these are some of the questions we had to ask. So was a very puzzling part of this project, but hey, we figured it out. We got out there. Next slide. And yeah, as Jordan mentioned, this detail became almost the bane of our existence. It was one of those conditions that was sort of a late change as well. So there was a purlin that was originally located on the interior side of this condition that ran continuously, sort of parallel to the length of the facade. And that got shifted to the outside. And that caused issues because we didn't really have a strategy defined for how to seal that area. And now what was happening is we had a penetration through our air barrier. And when we first arrived on site, we fired up the blower door fans. And, you know, one of the things that I'm realizing now, having done a lot of blower door tests, and especially on this project, is if you want to find air leaks in a building, just use your ears. That's one of the best ways to identify air leaks. And we could hear the first off, it was extremely quiet in the building. And that was like an amazing feeling to see how, or hear how loud it was in the surrounding industrial area and be in this like still environment. It was almost like, it was weird. And that's a huge part of the whole comfort equation and why we build house houses. But as we were walking around the building, we could hear whistling and louder sort of noises every 15 feet or so. And we were searching for hours. We could not figure out what the heck was wrong. And we found some small issues. We were like, this is not it. And then we like looked up at the roof at the underside and we like, well, I think we see daylight. Like, is that daylight on the other side of the roof? And you can sort of see it in the photo on the left there. There's some daylight coming through, and that was a condition that happened like 30 times in the building. And it was a huge chunk of leakage. When we had the fans running, we got up on a 15-foot ladder and stuck our hands up there, and you could feel the air blowing out. We're like, oh, we found, you know, at that point we were a bit over our threshold of 1 air changes per hour is the threshold for EnerPHIT. We were at like 1.1. So we were like, we got to find leaks. And we were like, this is it. This has got to be it. And the only problem was that it was a holiday. And it was a holiday where like no one did anything outside of just relaxing in town. So we had to go out and walk the streets and buy caulk and spray foam where we could and rally. You know, we tried to rally so many troops, but we only got a couple of people that were very gracious to come out on site from the local team and help us seal some of these areas. But we ended up sealing a lot of these areas ourselves to get these areas sealed. And you can see on the right, we just sort of gooped a bunch of foam in that corner to get the air leakage to be significantly reduced. And we actually were able to cut air leakage anywhere from 85 to 99% by sealing those specific conditions. And ultimately we passed. We tested in at around 0.76 ACH 50, I believe. So it was a huge accomplishment. We had to spend a couple extra days out there, but it was well worth it, well deserved by everyone on the team.
It was definitely, everybody went the extra mile. I mean, it was really, I mean, we were all freaking out a little bit, maybe a lot, but you know, definitely everyone was so committed to making this work. And I can't tell you how happy I was when we found out where the problem area was, because then there was at least something we could fix. So it was, you know, it was a great achievement, I will say, and definitely kudos to Dylan and Mike, who, you know, went way beyond what was expected.
Yeah, so this is a fun graph. So we got a full year's worth of utility data towards the end of 2017 into 2018 after the project was completed and in operation. And some exciting points of information here are that the building was consuming about 60% less than what it was consuming before, and actually even more of the savings if you look at what the building would be using in a conventional sense, because there was additional process load that went into the building. So big kudos on the energy savings side of things. And then what we're showing here in the dotted dash line, or the dash line, is the PHPP prediction. And we came in on average about 9% less than what the PHPP was predicting for that specific year. We're hoping to get more data. We had actually a whole monitoring package and equipment plan to be installed for the team to study different specific end uses for the project. And Coordinating that has been a big challenge, installing this equipment, and COVID really put a wrench in that as well. So we're hoping to follow up and try to actually start to get some more granular data and also get some of this higher level data as well to keep tracking. But signs are pointing in extremely positive directions from this.
All right. So I'm just going to quickly flip through some completion photos so you can see what it looked like. I mean, I think you got a good sense from the video probably. You know, here's a photo of the roof. And here we can see some of the solar shading screens, very basic, just perforated metal, painted. Here's kind of the back corner, and this is where a lot of the employees would actually go in. And so you can see that, you know, EFIS on masonry condition, and then some of those areas that are actually outside of the, you know, the treated floor area. We left the Aerolon yellow because the client liked it so much. He was really happy with that. So you can see little bits of yellow Aerolon everywhere. And this is the inside, and it's the nicest factory you've ever been in your life. You know, I mean, if you've ever had to work in a factory, this is the one you want to be in. It's quiet, the air quality is amazing, temperature is really nice, humidity is really low. I mean, it's definitely, you know, at the end of the day, like this is the thing that makes me happier than almost anything else about this project is we've created amazing working conditions for hundreds of people, you know, who previously would have been in much more miserable circumstances. So you can see the kind of rows of sewing machines that are all lined up along these power bus bars, and the LED lighting. And then, you know, another nice thing is there's really great natural daylight. I mean, all that glass actually, you know, does pay off in the end in terms of making it feel very open and airy. And this is actually looking through those perforated metal screens. You can see how bright it is actually outside. There's some office space as well. This is a pattern making area on the upper level. And then on the lower level, this is another design area where they like to keep the lighting a little darker. There's also a showroom on the ground floor, some other sort of collaborative design spaces, and the lobby. So, you know, it's definitely, you know, intended to be kind of a showpiece factory. So, you know, overall, everything is a little bit nicer than definitely you would see in a typical factory. But, you know, it's a real place where real work gets done. And that's, you know, that's very satisfying. So certifications, you know, through PHI, we got a pilot certificate, you know, mainly based on certifying the cooling loads. And that was an important way to kind of meet the threshold and criteria. And we can come back to this later if anyone has more questions. We found out actually independent of us, they went through the whole LEED certification process as well. And they managed to get LEED Platinum. So that was kind of exciting as well. So it got the double certification. And this was just the project team. And I think that is it. Thank you very much.